Hello students, welcome to the lecture. The topic that we are going to see today in rotational dynamics is conical pendulum. So what is a conical pendulum? It is nothing but a system where a mass is attached to a string. And the mass performs uniform circular motion. But the circular motion is in horizontal plane, and the string that supports the bob, it traces a right circular cone. So I've attached a figure on the left hand side of the page where you can see a conical pendulum. The string of the conical pendulum is L, has length L, and the mass of the bob is M. So I've already drawn the forces that are acting on the bob. The first force is the tension which acts along the string, and the second force is mg, that is the weight of the bob which acts vertically downwards. Now we can see from the figure that the weight is acting downwards, the tension is acting towards the string, and theta is the angle that the string makes with the vertical. So we can divide the tension over here into two components. Over here we have t cos theta, because this angle is also theta, and over here towards the center we have t sin theta. So t cos theta is upwards and t sin theta is towards the left. So if we have a look at all the forces that are acting on the bob, we can clearly see that the weight mg is balanced by t cos theta, and the component of the tension t sin theta provides the necessary centripetal force. So from this we have two equations. The first equation is t cos theta is equal to mg, and the second equation is t sin theta. As it is providing centripetal force, we can write it as mv square by r, where r is nothing but this radius. Now let's move ahead. So the two equations that we have with us are mg is equal to t cos theta and m omega square r is equal to t sin theta. How do we get m omega square r? Because t sin theta was providing the centripetal force mv square by r. Sorry, there's a capital R over here. Yeah. And we know v is equal to r omega. Therefore, in the place of v, we can write r square omega square upon r. R and r gets cancelled. So we have t sin theta is equal to m omega square r, where omega is nothing but the angular velocity of horizontal uniform circular motion performed by the bob. So we have two equations with us. Mg is equal to t cos theta and t sin theta is equal to m omega square by r, or m omega square r is equal to t sin theta. So let's divide the second equation by the first equation. So we get m omega square r upon mg is equal to t sin theta upon t cos theta. M and m gets cancelled, t and t gets cancelled, and we have omega square r by g is equal to sin theta over cos theta. Now let's write r in terms of length L. So from the diagram we can see that sin theta is opposite side r upon hypotenuse L. So r can be written as L sin theta. Now let's plug this value of r into the equation. So omega square L sin theta upon g So omega square L sin theta upon g is equal to sin theta over cos theta. Sin and sin gets cancelled. So we have finally omega square is equal to g upon L cos theta. And from here we can write down omega is equal to under root g upon L cos theta. Okay. We have seen in the earlier lectures that there is a relation between time period and angular velocity, and that is nothing but time period t is equal to 2 pi by omega. So if we plug the value of omega in this equation, we get 2 pi upon under root g upon L cos theta as the formula for t. And now if we rearrange the terms, we get the time period as 2 pi into under root L cos theta by g. So this is the formula for time period of a conical pendulum. Time period of a conical pendulum. And in this formula, t is nothing but the time period. Then L is nothing but the length of string. Theta is nothing but the angle between string and vertical. And g is obviously nothing but gravitational acceleration. Okay, so thus we have derived the formula for time period of conical pendulum, which is nothing but t is equal to 2 pi under root L cos theta over g. Okay, let's move on to the next topic, which is nothing but vertical circular motion. So it is nothing but a circular motion performed by the particle in vertical plane. And the best example is that if we have a stone attached to a string, and if we whirl the string in vertical circle, the stone moves in a vertical circle, and that is nothing but the vertical circular motion. Now, I have drawn a free body diagram of the stone which is attached to the string and moved in vertical circle. So on the left hand side of the page, you can see the free body diagram, and it shows all the forces acting at different positions during the vertical circular motion. So in this vertical circular motion, what they ask us is generally to derive the formula for minimum speeds at different locations. And which minimum speed? Such that the bob just completes the circle. So the positions that are important to us are nothing but the bottom position B, the top position A, and the mid positions along the horizontal diameter, that is nothing but C and D. So let us see how to derive the magnitude, or how to find out the magnitude of minimum speeds for these different locations when the particle moves in a vertical circle. We start with the topmost position. Which is nothing but point A. Now, what do we do over here is first we write down the equation of forces at point A. So at point A, we can see that tension as well as weight act towards the center, and thus they both provide the necessary centripetal force. So we can write down TA plus mg is equal to mva square upon r, where r is nothing but the radius of the vertical circle. Now, if we want to find out VA minimum, the left hand side, that is TA plus mg, should also be made minimum. And we know that mg is constant, it cannot vary. Therefore, the only thing that can vary is tension. And therefore, for minimum velocity, the tension at point A should also be minimum. Now, that minimum tension is nothing but 0. So, plugging this value, 0 plus mg is equal to m VA minimum ka square upon r. And cancelling the m, we get VA minimum is equal to under root RG. VA minimum is equal to under root RG. So this is the minimum speed of the particle at the topmost point if we want to complete the circle. So at the topmost point, to complete the circle, the minimum velocity of the particle or the mass attached to the string must be under root RG. Now, after this topmost position, let's move on to bottommost position. So let's move on to bottommost position. Okay. At bottommost position. Most bottom position. Okay. And we know that it is nothing but point B. So first, what we will do is we will change the methodology in which we are finding out the minimum velocities. Over here, now we are going to use energy conservation. Energy conservation. Because gravity is a conservative force, and therefore total mechanical energy is conserved. And since total mechanical energy is conserved, we can write down kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. Here, the initial point is A and final point is B. Our initial point is B and final point is A. So, initial point, let's consider B. So, kinetic energy at B plus potential energy at B is equal to kinetic energy at A plus potential energy at A. Now, kinetic energy at B, we can write down half mvb square, and the potential energy can be taken 0 once we define B to be base, B to be at base, and at base, the potential energy is 0. So, at A point, the kinetic energy is half mva square plus potential energy is mgh, and we can clearly see that from the base, the point A is at a height of 2r. So mg2r. So what we get is half m vb square is equal to half m va square plus 2 mgr. We cancel m from everywhere. Now we know that 2g and r are constant. Therefore, to find out the minimum velocity at point B, the velocity at point A should also be minimum. So vb minimum square upon 2 is equal to va minimum square upon 2 plus 2gr. Now we know that A is nothing but the topmost point, and the minimum velocity at the topmost point we just derived now, and it is nothing but under root rg. Under root rg. So when we substitute this value, we get vb minimum square upon 2 is equal to va minimum square is nothing but rg, or let's write it. Again and again writing a small r. Sorry, there should be a capital R. Yeah. rg gr upon 2 plus 2gr, which is nothing but phi gr by 2. This 2 and this 2 gets cancelled. And finally, we have vb minimum is nothing but under root phi gr. Under root phi gr. So, at the bottommost point, the minimum velocity that we have is under root phi gr. Minimum velocity at bottommost point. Bottommost point. Now the last point remains, that is nothing but minimum velocities at midpoints, which is nothing but C and D. So the magnitude of velocities at C and D, it's same, but the directions are opposite. Which means that if the particle is moving upwards at point D, it will move downwards at point C. Okay, now I'll just erase out the forces. Okay. So again, we can use energy conservation because the force acting is gravity and it is a conservative force. So we can conserve energy. But now we will conserve the energy at one of the midpoint. Let's consider point D and the bottommost point, that is B. So obviously, according to the energy conservation equation, kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. So initial point, let us consider B. So kinetic energy initial is half mvb square. Potential energy initial is 0. Then kinetic energy final point we will consider D. So half mvd square plus mg, and the height is r. The height of point D is nothing but r. Now, if we want the minimum velocity at point D, we need to plug in the minimum velocity at point B. So half m vb minimum square is equal to half m vd minimum square plus mgr. Let's cancel the m's first. We just derived the formula for vb minimum, and vb minimum what we got was under root 5rg. Under root 5rg. So let's plug the value. So over here we have under root 5rg is equal to half vd minimum square plus gr. So half vd minimum square is equal to 5 by 2 gr minus gr, and that is nothing but 3gr by 2. 2 and 2 gets cancelled, and we finally get vd minimum, which is equal to vc minimum in magnitude, is nothing but under root 3gr. Under root 3gr. So we have found out the velocities, the minimum velocities at all the points of the vertical circle, so that the particle which is performing vertical circular motion just completes the circle. So we will just plot quickly the velocities, minimum velocities at the desired locations and their directions on this diagram. So let's assume an anti-clockwise vertical circular motion. This was point A, this was point B, this was point C, and this was point D. So at point A, the velocity will be towards left, and we have VA minimum is equal to under root RG. Under root RG. Then at point C and at point D, the velocities are just in opposite direction, but their magnitudes are equal. So VD minimum is under root 3RG and VC minimum is also under root 3RG. And at point D, we have, at point B, that is the bottommost point, we have VB minimum is equal to under root 5RG. Okay, so these are the minimum velocities at the different locations, which is the topmost point, the bottommost point, and the midpoints. At topmost point, the minimum velocity is under root RG. At the bottommost point, the minimum velocity is under root 5RG. And at the midpoints, the minimum velocity is under root 3RG. We have two midpoints. The magnitude at both the midpoints for the velocity is same, only the directions are opposite. Thank you.